Okay, today's goal is to sketch rational functions. We're going to sketch two functions today. The first function is f of x equals 3x minus 12 over 2x plus 5. I'm going to start by factoring because we learn a lot by looking at the factored form of the function. For example, I see the denominator does not factor and no factors cancel out. Therefore, I can already conclude that there are no removable discontinuities. Those are discontinuities that come from factors that are removed or canceled out when you simplify. I can also tell that the denominator can't be 0. We cannot divide by 0, so x cannot be negative 5 halves. That means I have a discontinuity where x is 5 halves, and so that discontinuity must be a vertical asymptote, since the only other option was removable discontinuity. So there's a vertical asymptote at x equals negative 5 halves. Now I also want to look for horizontal asymptotes. When I'm looking for horizontal asymptotes, I'm thinking, how does the numerator change in relation to the denominator? And I see that both the numerator and denominator are linear, so they'll grow at about the same rate. So eventually, we'll approach the ratio of leading coefficients. So we have a horizontal asymptote at y equals 3 halves. In addition to finding asymptotes and removable discontinuities, I want to find intercepts. So I know that x-intercepts have the y value 0, and so I'm going to substitute it in 0 here. Now this is just a rational equation, which of course I can solve by getting a common denominator, in this case 2x plus 5. Once I have a common denominator, the numerators must be the same. Now, of course, 3 is never going to equal 0, so that doesn't provide a root, but x minus 4 will equal 0 if x is 4. So this function has one root at 4, 0. Let's find a y-intercept now. That's where x is 0. So we have f of 0 equals 3 times x minus 4 over 2x plus 5. Oops. Only f of 0 implies I'm substituting 0 in for x. So I have 3 times negative 4 over 5 is negative 12 fifths. So I have a y-intercept at 0, negative 12 fifths. Okay, let's put all these pieces of information together. Let's plot our roots and intercepts. This graph does not have to be to scale. I don't care about that at all. I just care that you're plotting and labeling the key information. Vertical asymptotes and horizontal asymptotes get plotted with a dashed line. The dash indicates you're never actually going to reach that value. All right, let's connect the dots. Now, let's start with this rightmost piece. If I'm at the root and I'm moving to the right, I have to get closer and closer, but never intersect this asymptote. That's what an asymptote means. It's a line you approach or get really close to, but never intersect. Let's connect these with a curve. I'm going to go back and straighten it out a little bit. Okay, and now if I move to the left of negative 12 fifths, I'm also going to approach this asymptote, this time the vertical asymptote. So I'll get closer and closer there. Now on the left side of the vertical asymptote, there are a couple options. Either, I'm going to extend my graph, either I'm going to be above the asymptote, the horizontal asymptote, it'll look like this red piece, or I'll be below. And I know it's going to look like one of these two things because as x values get really tiny, I have to approach the horizontal asymptote. That's what it means. It's an end behavior. And as you get close to the x value, negative 5 halves, you have to approach this asymptote. Well, it can't be the blue section because you don't have a root to the left of negative 5 halves. So it must look like this red and green piece. Here is your sketch. Okay, the next function that we're going to sketch today is this. I'm going to start by factoring. I notice the denominator has an x in both terms, which can actually be further factored. I notice the numerator has a leading coefficient other than 1, so I need a 2x and an x. Let's try 5 and 3 to get that 15. If so, I've got a 5x and a 6x. Ooh, well, we can make positive 1 if we subtract the 5x from a positive 6x. So that'll work. So I have 2x minus 5 over x plus 3. I always start by simplifying because then you can use the simplified version. Because I see that I've got an x plus 3 in the numerator and denominator. This is producing a whole, a removable discontinuity. And so aside from taking a note right here that we have a removable discontinuity, we can use this nice simpler version of the function. So let's make that note. I can see that from the factored form that I have vertical asymptotes at x equals 0 and x equals 3. 2 of them this time, that's interesting. And I can see that I have a horizontal asymptote at, well, let's see. In the simplified version, my degree in the denominator is larger, it's 2, than the degree in the numerator, which is just linear. If the denominator goes faster, you're dividing by really big numbers, so the fraction as a whole will approach 0. Let's find the intercepts next. To find an x-intercept, I'm going to set y equal to 0. And once you get a common denominator, we can put that 0 over 1, of course. If you get a common denominator, then you set the numerators are equal. And so we find the x-intercept. To find the y-intercept, I'm going to set x equal to 0. This is nice. I'll use that simplified version of the fraction. And I get something that's dividing by 0, which you cannot do. And so we conclude there is no x-intercept. And now it's time to put these pieces together. Let's plot. This is interesting. We've got a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0, and another vertical asymptote at 3. Oh, I'm sorry, we've got a removable discontinuity at 3, right? Oh, I made a mistake, I'm sorry. Our removable discontinuity is at -3 because it's coming from where x plus 3 is equal to 0, that factor that canceled. Okay, now I'm going to plot my intercepts. The only intercept I have is a root at 5/2. Okay, from here, the function can either look like this and approach the vertical asymptote going up or down. You'll have to find a test value to prove it. So you need to choose an x value that's between here. So an x value between 0 and 5/2. If you choose f of 1 and substitute it in, you get 3/2. So that must mean we've got a positive x value here. Again, you need an x value between 5/2 and 3 to see if you're going up to meet the vertical asymptote or going down. When you try f of 2.9, you get a negative number, which means you've got to be going down. You need test values to know if you look like this or this, and test values to know if you look like this or this. I will leave it to you to choose a test value greater than 3 and a test value over here to decide which of the 2 blue pieces is in the function and which of the 2 green pieces is in the function. We'll discuss in class.